example TryIts that go with the 1-4 student companion on inductive reasoning. So look at example 1. Use inductive reasoning to extend a pattern. So what appears to be the next two terms in each sequence. If we notice 1a, 800 to 400, it looks like 800 divided by 2 gives me 400, and 400 divided by 2 gives me 100. 100 divided by 2 gives me 50, and so on. So the pattern is to divide by 2. The next 2 would be 50, and then 25. And then it would keep on going, like 12 and a half, and so on. Looking at number B, 1B. This one is a little bit different. In looking at this, I see that 1/3 of 18 is 6. If I add that to 18, I get 24. 1/3 of 24 is 8. If I add that to 24, I get 32. 1/3 of 32 is a number that when I add it to 32 gives me 128 over 3. Let's check it out and make sure that it works that way. So 18 divided by 3 gives me 6, and 6 plus 18 is 24. 24 divided by 3 is 8, and 8 plus 32 is, or 8 plus 24 is 32. Now if I take 32 divided by 8, or 32 divided by 3, and add that to 32, let's see what we get. We have to go for common denominators. So we have to do 32 over 3 plus 96 over 3. And when we add those together, we get 128 over 3. So 128 over 3 generates this sequence here. So I take 1/3 of 128 over 3, which is 128 over 9, and I'm going to add that to the one that came before, which is 128 over 3. I have to get common denominators again, so I'm going to have to multiply the second one by 3. I have 128 over 9 plus 384 over 9. That's going to give me 484, 504, 512 over 9 for my next term. And then we need to do it for one more. So I'm going to do 512 over 9 divided by 3 gives me 512. Same thing as multiplying by a third over 27. I'm going to add that to 512 over 9. I'm going to have to multiply the second one by 3 over 3 to get common denominators. So I have 512 over 27 plus 1536 over 27. And add those together, I get 2048 over 27. And then we could continue the pattern on the same way. Okay, let's look at the chart that goes with example 2. Let's see. So the first term is a 1. Second term has, so we have one row of 1. The second term is 2 rows of 2 plus 1. The third term is 3 rows of 3 plus 2. The fourth one is 4 rows of 4 plus 3. So my conjecture is that the next one's going to be 5 rows of 5 plus 4. So the number of dots, the conjecture might be like if n is 1, we have n squared plus n minus 1. See how that works for 1. So n squared, if n is 1, we have 1 squared, which is 1, plus 1 take away 1, which is 0, so we're left with 1. Put a 2 in, we have 2 squared, plus 2 minus 1, which gives us 4 plus 1, which is 5. Put a 3 in for this, we have 3 squared, plus 3 minus 1, which is 2. That's going to give us 11, which goes with the third one. So I'm pretty confident in this conjecture. And so this is going to be the rule that deals with the nth number of the pattern. Let's say we were talking about 10. We'd have 10 squared plus 9, which would be 109. If we did the fifth one, we'd have 5 squared plus 4, which is going to be 29. So the next one would have 29 dots in it, and so on. Let's look at example 3. Based on the data about how many members would you expect the chess club to have? Now this is one where in its 5th year we can just continue the pattern on. We can also find most likely a rule for this. Each one of these is going up by 4. Well, this last one's going up by 5 though. Let's see. This one goes up by 3. This one goes up by 4. This one goes up by 5. The next one, to continue the pattern, is going to go up by 6. So the 5th one would have 28. And they're not asking us about a rule for this one, but if we were looking for a rule, since it takes 2 levels down to get to the constant difference, this is going to be an n squared type pattern, like an n times n pattern, and we could guess and check the numbers for that. But it's not asking us for the rule, it just wants us to find out what the next number was in the sequence. Let's look at example 4. Find a counterexample to show a conjecture is false. What's a counterexample that shows the statement the sum of 2 composite numbers must be a composite number? Now, a composite number means it's composed of 2 other numbers. So, like a number like 6 is a composite number because that's 2 times 3. So, to find a counterexample, we need to find an instance where 2 composite numbers actually make a prime number. So let's see. So a prime number would be 11. Let's see if I could think of 2 composite numbers that make 11. 4 and 7 doesn't work. 6 and 5. 9 and 2. Can't really do it for 11. Let's check it for 13. 4 and 9 makes 13. So 13 is a prime number, which is not composite. 2 composite numbers could be 4, which would be a 2 times 2, and a 9, which would be a 3 times 3. Those are 2 composite numbers that add up to a number that is not a composite number. So that shows that since this is a counterexample, my conjecture must be false. Now, if I could not find a counterexample, then I would have to assume that my conjecture was true. Okay, let's look at example 5. For each conjecture, test the conjecture of several more examples or find a counterexample to disprove it. For every value n, the value of n squared is positive. Let's check it for, we got different categories of integers. We could think about negative integers, we could think about 0, and we could think about positive integers. So if we take 2 negative numbers, like say negative 3 times negative 3, that gives a positive 9. If you take 0, multiply 0 times 0, we get 0, which we assume is also positive. And if we take, say, a number like 3, which is a positive number, times another positive number, we get 9. So I can't find a counterexample where if you square an integer, you don't get a positive result. So I'm taking this conjecture to be true for part A. So for part B, a number is divisible by 4 if the last 2 digits are divisible by 4. This is actually a rule for divisibility by 4. So let's look at a number like 128. The last 2 digits, let's look at 128. If the last 2 digits is by 4. 28 is divisible by 4. That gives us 7. So that means that 4 should go into 128. And it does. It goes 32 times. Let's try a negative number. Let's try like negative 188. Let's see. 88 is divisible by 4. It goes 22 times. So let's check and see if we can divide 4 into negative 188. 4 times a negative 40 makes 160. 28 left over. And a 7 makes the 28. So this also appears to be a true conjecture. I can't think of a counterexample where the last 2 digits are divisible by 4, yet 4 doesn't divide the number. And that really works because the hundreds part or the thousands part divided by 4 is going to be like 25 or 250. So the last 2 digits really kind of determine whether or not the number is going to be divisible by 4. And that's it. Thank you.